going to be looking at limits at infinity here. And we're going to determine finite limits at infinity and determine horizontal asymptotes, and then infinite limits at infinity as well. So we'll look at graphically and then analytically as well. But the big thing on this one is if you can reference what you learned a little bit in pre-calc, we're going to be talking a lot about this idea of in behavior. And so in behavior, we tied in pre-calc to horizontal asymptotes. Here, we're going to use limits to determine in behavior, but it's going to be the same. It's going to be tied with horizontal asymptotes as well. And that's what you can see in our second objective. So when we're determining the limit as x approaches either infinity or negative infinity, we're attempting to identify the value at which the graph seems to be heading towards. So is it flattening out to some y value, in other words? And so graphically, if you look at sort of what we're seeing here with the 3 over x minus 2, as x approaches infinity, notice it seems like it's getting really and really close to the x-axis, which means my y value is 0. And as I approach negative infinity, which is in this direction, so if I keep going to the left, then notice once again, it looks like it's arbitrarily getting very, very close to 0 again. It will never get horizontal. It's always going to be getting closer and closer forever and ever, but it'll never get to 0. It's just that that's what we're approaching, which again, it goes back to what limits are asking us. So a good rule of thumb and some things that want to get down is what's in yellow here. The limit as x approaches infinity and the limit as x approaches negative infinity of 1 over x. Now, this is a very general sort of scheme, but we're going to be using this idea. And both of these would end up being 0. Now, the question is like maybe why? Okay, so I want to address that really quickly, and then we'll go on to looking at some things. Well, if you think about it, it doesn't have to be 1. It could be a variable up there as well, but if the 1 or if the numerator is smaller than the denominator, and the denominator increases at a faster rate than the numerator, okay, so right here the numerator may be increasing, but the denominator is increasing quicker. Okay, so now obviously if the numerator stayed the same and the denominator is increasing, it's even more so. But what you'll notice here is if you plug these into your calculator, if you do these in your head, what we're doing here is the question is what value are we approaching? So as we do all of these, I can't get that 0. There we go. Okay, so like 1 over 10. If we go ahead and let's say, we're like, okay, well, let's do the decimal representation of this. So 1/10 would be 0.1. Okay, but now if you do 2 100ths, then what you get is 0.02. There we go. And 3 1,000ths. So now we got to go way out here. And then 4 10,000ths. And so we got way out here, something like that. And so notice that the value, the overall value, it's like, what are we getting closer and closer to? And that idea is 0. We'll never get there because the numerator is not 0. Even if the constant's on top, it'll never be 0, but that's what we're approaching. So we're going to be using these two concepts right here quite a bit. Let's go ahead and look at some of the sort of notes. This is a flashcard stuff, so with the star here. So there's really 3 things. So what's in red, or what's in blue, excuse me, is what we're going to be looking at. That would be on our flashcards. But what we have is if you're trying to find a limit as x approaches infinity or negative infinity, what we want to determine is the degree of the numerator and the degree of the denominator. And the reason is that the degree, whatever the largest degree term is, dominates the behavior of that part of the function. So if the degree of the top is 2 and the degree of the bottom is 3, now what we have is we can determine which one's growing faster than the other, the top or the bottom, or are they growing at a relative similar pace? So that's what we do with the degrees. So number 1, if the degree of the bottom is bigger than the top, okay? So the degree of the bottom is bigger than the degree of the top. So what you have is a little top and a big bottom. Big bottom. All right. So if that's the case, and again, how I determine that is, first off, how we do this is we go and we say, oh, the limit as x approaches infinity. And what we want to do is go, well, what do we look at? Degrees. Okay, so that is just, it's really a regurgitation, it's a memorization, but the limit as x approaches infinity deals with in behavior. So what we want to do is we want to determine what the degrees, if we can, of the numerator and denominator are. Okay, and so the degree of the numerator is 1, degree of the denominator is 2. So that means the degree of the denominator is larger than the degree of the numerator. And so anytime that's the case, if we have little over big, that's always going to equal 0, just like what we just did with 1 over x. So it's just that memorization thing. So the limit as x approaches infinity or negative infinity of a little over big, 0. Now, what if the degree on the top's bigger than the bottom? Now the top's the big one, and the bottom one's the little one. So the big one's on top. And then we got the little one on the bottom. Now, if that is the case, now what we have is, just think of it intuitively. If the top is growing very quickly and the bottom is not growing as quickly, the overall value is getting very, very large in one of two directions, either towards infinity or negative infinity. So our answer to these are either going to be infinity or negative infinity. So once we determine, we go, oh, the limit as x approaches infinity, I look at degrees, 3 and 2. Degree on the top's bigger than the bottom. That's either going to be infinity or negative infinity. Now, how I determine which one it is through the signs. Okay, so let me show you what I mean by that. If x approaches infinity, that means x is a positive value. So just treat it like a positive infinity. So we have positive infinity cubed. Well, positive infinity cubed is positive infinity. So positive times 2, positive, plus 5, positive. So we got a positive infinity on top. If you look at the bottom, we plug an infinity in, a positive one. Positive squared, well, anything squared is positive. So we got positive times 9, positive, plus 1, positive. So we get positive over positive. So we have positive infinity as our limit. Looking at the exact same function, but this time approaching negative infinity. Okay, so we know here that the degree on the top is bigger than the bottom. So we know it's either infinity or negative infinity. We got to check the signs. Well, now I'm plugging in negative infinity. So think of it as negative infinity. What's negative infinity cubed? That would be negative infinity. Negative times negative is positive times another negative is negative. So we have 2 times negative infinity, which is negative infinity, plus 5. Well, I'm sorry, 5. You're not going to cut it. The numerator is going to be negative in this case. Okay. In the denominator, what's a negative infinity squared? Well, I just had mentioned anything squared is going to be positive when we talk real values. And so here what we have is 9 times positive infinity, which is positive infinity. Plus 1 is positive infinity. And so we get negative over positive, which is negative. And there's our value for that. What if the degrees are the same? Because things would sort of grow similar, at similar rates at least. And so when we have a situation like that where the degrees are the same, really what we're going to do is we're going to look at the leading coefficient of the degree term on the numerator over the coefficient of the degree term in the denominator. And so in this case, the degree is 2 on top and the degree is 2 on the bottom. And if I'm finding the limit as x approaches infinity or negative infinity and the degrees are the same, then my value is going to be that ratio, 2/3. Isn't that pretty nice? That's a quick way of doing it. Now, why that works, I want to show you why that works. Okay, and I'll do it very quickly. Okay, but here's the reason why. I want to use that concept of a little over big being 0. Okay, so remember, little over big is 0. So if I divide everything by the largest degree, and the largest degree was x squared. So I'm going to take the numerator and divide everything by x squared. I'm going to take the denominator and divide everything by x squared. So 3x squared over x squared and 1 over x squared. So as long as I do everything to top and bottom, I'm good. And now we go ahead and we simplify everything. We get 2 plus 5 over x squared and 3 plus 1 over x squared. Now, if I plug in infinity in this case, 5 over infinity squared, little over big, that's simply 0. And then 1 over infinity squared is definitely going to be the same thing. It's going to be a 0, and so you can see where the 2/3 comes from. Okay. Now, we're going to practice each one of these, then we'll go into horizontal asymptotes to wrap things up. And so here we want to find the limit as x approaches negative infinity. So as soon as you see or hear that, you want to think degrees, if you can find it. So the degree of the numerator is 5, and the degree of the denominator is 6. So if the degree on the bottom is bigger, than the top. So you got little on top, big on the bottom. So anytime you have little on top and big on the bottom, that's a no-brainer. Then what we have is not D. Looks like a D. Okay. 0. Okay. Looking at the second one, the limit as x approaches infinity. What do we look at? Degrees. What's the degree of the numerator? 4. What's the degree of the denominator? 4. If the degrees are the same, what do we look at? Leading coefficient. So 3 over 3. And then hopefully you just simplify that best you can, and so that would come out to be 1. So our value for that limit is 1. Looking at the bottom one, we have a limit as x approaches infinity. What do we look at? Degrees. What's the degree of the top? 2. What's the degree of the bottom? 1. The degree on the top is bigger than the degree on the bottom. That means it's either going to be infinity or negative infinity. Just depends on the signs. So what we do is we take whether it's infinity or negative infinity and we plug it in. So positive infinity squared is positive, times 2 is positive. Now, so we have, I want to make sure we understand this because 4 times infinity is infinity. But infinity times 4 is not as big as infinity squared times 2. So I know this seems really weird, but we got like a bigger infinity than the other infinity kind of thing. And so when you have a big infinity minus a small infinity, we should have a positive because we're not taking more than what we started with. Okay, I know that's weird, but that's how we do it. Looking at the denominator, we have infinity plus 1, which is just positive infinity, so that one's pretty easy. So we end up just getting positive infinity as our answer for that. Okay. Now let's look at a really quick, a weird one, and that is one where let's say the denominator or the numerator, but definitely in this case, the denominator is not a polynomial, so it doesn't have a degree. It has a radical. So how do we handle this? So there is sort of a fuzzy math cheater's way of doing it, and I'm going to show you that. Most of us are probably going to end up using the cheater's way of doing it, but I want to make sure you understand really the math behind it and why we can sort of cut some corners there. What we do is the limit as x approaches infinity. So x in this case is approaching positive infinity. That means the x is positive. Okay, if we come up here and take a look, the square root of x squared, you probably remember even from algebra classes where those cancel each other out and we get x, right? Now, we want to be very careful here, though, is because the x value that's inside of this has to be the same as what's outside. See, they're the same x here. So if we started with a positive x here, then this needs to be a positive x there. Right? It makes sense, right? So in this case, we did. So there's really nothing too unique about that. So when x is positive, what we're going to use is this idea of the square root of x squared being x. Right? And I'll show you why in just a moment. But I also want to show you this and make sure it makes sense. If my x is approaching negative, that means my x's are negative. So remember, this x is negative, but when I square a negative, it makes it positive. So when I take the square root of, let's say, 16, we get positive 4. We always do the principal root. But the x value has to be the same. So whatever I get here, 4 out of the square root of 16, I got to have the opposite of that so that this thing can stay negative. So when x is negative, we got to make sure we do the opposite of the square root of x squared. So that's a very unique thing, probably new to a lot of us. And so let's go ahead and explore this idea. So what I'm going to do is a little bit what I did earlier, where I'm going to divide everything by the largest degree. Now, even though the denominator doesn't have a degree, I'm going to use x. I'm just going to divide everything by x because the degree of the numerator is 1, so just x. So I'm going to divide it by x, the 2 by x, and I'm going to multiply the radical by x as well. Now, the numerator is perfectly fine. You guys will do fine. You can definitely start to see where the 3 comes from. Well, I haven't told you the answer, but where 3 is going to be our numerator because 2 over infinity is going to be 0. So there's the numerator. It's not bad. But the denominator is the one that gets a little tricky because I can't divide a radical by a non-radical. So I need to rewrite the x in the denominator using a radical. So come up here, and we have 2 choices. Either x equals the opposite of the square root of x, or x equals the square root of x squared. So it's like, well, which one do I choose? It depends on, is your x positive or negative? If your x is positive, then what we can do is replace x with the square root of x squared. So this is what it would look like. And so we get here, And then instead of x, we can have the square root of x squared. Now, in the next example, notice that x, so we're going to end up doing the same thing for this problem over here. So I'm just going to go ahead and write where we're at. So we get 2x squared plus 1. And again, we divide by x. And so here's the difference. Over here, the x was positive, so I'm going to use the square root of x squared to replace the x. Over here, the x is negative, so I don't want the square root of x squared. I want the opposite of the square root of x squared, because I have to make sure that value is going to be negative, the x value. So if I go ahead and simplify using my quotient property of radicals, the denominator, this first problem that we have, what we have is we have a huge radical where 2x squared plus 1, and then that x squared is just underneath each 1. And those are going to cancel. And so what we end up getting is we end up getting 3 minus 2 over x. And then in the denominator, what we have is the square root of 2 plus 1 over x squared. All right, now here's where we get our final answer. As I approach infinity, so I'm going to plug infinity in here. So as I plug infinity in, what's little over big, that's simply 0. On the bottom, I've got 2 plus, now again, what do we have? Little over big, that is simply 0. And so our final limit value is 3 over the square root of 2. If you rationalize, it'd be 3 squared to 2 over 2. You're really going to end up getting the same thing. The only difference between this one and that one is the negative sign that we put. And so we end up getting the 3 minus 2 over x. And then here what we get is the opposite of the square root of 2 plus 1 over x squared. So once I stacked it, okay, it's called the quotient property of radicals. Now if we plug in, let's say, negative infinity, okay, what we get is we get 2 over negative infinity, which is 0. And the negative infinity doesn't change anything, just the other direction. Then we get on the bottom, we get the square root of 2 plus 0. And so what we end up getting is 3 over the opposite of the square root of 2. Okay? And so that would be our limit for this problem. Now, here's the shortcut. I'm going to erase all of that, and I'm going to show you the fuzzy math. Here's the fuzzy math. When you recognize this, and we go, oh, I want to look at the degrees, and you're like, well, wait a minute, the bottom one doesn't have a degree. Well, okay. Yeah, so here's the cheat. Take everything out that's not going to have to do with the degree of the numerator and degree of the denominator. So leave the largest degreed terms in the numerator and the denominator. Okay, so it looks a little bit like this. Now what I can do, and you'll end up doing this in your head a little bit, is if I go ahead and sort of split this bottom one up using the quotient the product property of radicals, you end up getting this right here, because the square root of 2 times the square root of x squared. And then the square root of x squared is, and especially when x approaches infinity, is going to be positive x. So now they have the same degree, and what do you do when you have the same degree? You look at the leading coefficients, and there's our answer right there. You can see why students just sort of do the fuzzy math, because it's much quicker. Same over here, but we still have to remember that when we get this, and we have 3x on top, and then on the bottom, what we have is the square root of 2. But what we've got to remember is that when x is approaching negative infinity, we have to throw a negative on there, because that negative goes with the x, whether it's with the square root of x squared when we do it the proper way, or when we write it like this, we have to have that negative. And so there's the negative 3 over the square root of 2, or negative 3 squared to 2 over 2 if you rationalize. These are 2 answers. Last thing we'll take a look at is horizontal asymptotes. And so in this case, we're going to find a horizontal asymptote. So how do we find it? We find the limit as x approaches infinity and the limit as x approaches negative infinity. Now, I would say most of the time, and I mean most, I mean probably like 90–95% of the time, those are going to have the exact same values for what we're doing. However, that's not always the case. So let me give you just a real quick picture of when that's not the case. So let's say that's 1 right there, and this is negative 1. And let's say my graph did something like this. Okay? So if I said, what is the limit as x approaches infinity, it would be 1. But if I said, what's the limit as x approaches negative infinity, my answer would be negative 1. So there are times where we have multiple horizontal asymptotes. So when we are trying to find horizontal asymptotes, we need to check both going to the right and going to the left to make sure that they are, and again, typically the same, but making sure they are the same. If they're not, then we would have two horizontal asymptotes, and that's perfectly appropriate. So what this says, and what I'd fill into the blank here, is simply this. If I find the limit as x approaches, let's say, infinity of a function, and it equals b, or the limit as x approaches negative infinity of a function, and let's say it equals b, then y equals b is a horizontal asymptote. So what we can do is we can write an HA as simply y equals whatever that b value is. Now, just to show you sort of one type of question that they have like on AP stuff, it says, for x is greater than or equals 0, the horizontal line y equals 5. So horizontal is an asymptote. So they're giving us y equals 5, and they're calling that a horizontal asymptote. Now, they didn't come out and say horizontal asymptote. They said a horizontal line that is an asymptote. But that's an HA. So we want to connect that immediately. We go, well, if that's a horizontal asymptote, what does that imply about the limits? That means the limit as x approaches infinity or negative infinity of whatever the function is we're talking about, in this case f of x, would have to equal 5. That's how we find horizontal asymptotes. We find the limit as x approaches infinity and negative infinity. So if they're telling me the result is 5, then I know this statement has to be true, which you can see the answer is E. Now, some students mix up D just because the infinity and the 5 are in different places. So, until you get sort of a lot of practice, sometimes we mess that up. The other ones, though, don't make a lot of sense. We don't know them to be true. And again, it says must be true. They could be true, but we don't know. F of 0 equals 5? I have no idea. Okay? No idea on that. Could be, but we don't know. F of 5 is undefined. Okay? We don't know what f of 5 is. We don't even know what the function is. We just know that the function hugs 5 as we go out to the right or to the left. In this case, since x is greater than 0, we're talking out to the right to infinity. Now, I will say B is sometimes gives students trouble because they think horizontal asymptotes are like vertical asymptotes. And they think it has something to do with undefined values. It has nothing to do with undefined values. It deals with in behavior. So the name of it makes it sound like it's similar to a vertical asymptote, but the function can equal 5. I'm not saying it does, but it can. And so a good example of this is, let's say this is 5 right here. Maybe my graph does this. It hugs, pops out, and then does this, and then it hugs again. And so what we have is with horizontal asymptotes, it has nothing to do with undefined value. It has everything to do with in behavior. So f of x could equal 5. We don't know that for sure. And it says what must be true. So be careful of that as you're going through doing horizontal asymptotes.